I give some plan. Our plan is the following. The first point is we are going to discuss a Reedy model structure in topological spaces setting. Reedy model structure in top. The second point is the same in simplicial model structure. Simplicial model category. Sorry. The third one is Reedy category. Reedy categories in general setting and Hirschhorn's Hirschhorn's lemma. The next point is Reedy model structures and Kahn's theorem. And the last point is about applications. Okay, now we start with the Reedy model structure in top. Reedy. And now I'll give some example. Suppose we have the following filtration by skeletons. You know, if you have simplicial object in the category top, you can form the following diagram, and the nth term is just the following tensor product. Okay, and the question is, what is the case when the co-limit preserves weak equivalences? And it turns out that in the category top, the question, the answer is positive, and it follows from the following construction. We know that skeleton can be constructed from the following push-out diagram. So consider the following diagram, where these things means that this is a union of all degenerate maps. We can consider the union of all degenerate maps, and thus we can glue by this term this n-1 skeleton with the product of n simplex and xn, and we will obtain n skeleton of the realization of X. Okay, where this map is just a push-out coproduct. Where IM is an obvious inclusion, and the second map is a so-called latching map. And this guy is called latching object. Latching object. And this is a latching map. Okay, and we notice that this inclusion in top is, of course, a collaboration. And also this latching map is also cofibration. So the push out of cofibration is also a cofibration, and we have that this arrow is a cofibration, and in this sequence we have a sequence of cofibrations, and of course each terms of this sequence of this diagram is also cofibrant because we are in the top setting. So this diagram, for this diagram, homotopy colimit is the same as a usual colimit of this diagram. So we will obtain that the colimit construction in this case preserves weak equivalences. So this functor preserves weak equivalences in this case. As this diagram is cofibrant and by the, for example, Gambino theorem or the other, we will obtain the result. Okay, now consider the next case. The next case is a simplicial model category setting. Model category setting. In this case, we can define intuitively what is the matching object of a simplicial object. Suppose we have some simplicial object X, and M is a simplicial model category, and matching object, the nth matching object, is such object together with a map from Xn to Mnx, and this is a so-called boundary data. You can imagine that you take some you take boundaries of simplices and the union of such boundaries forms the latching object. And okay, you know that weighted limit with the weight delta n is just the set of n simplices. As you know, that is the same as and over n, and for x as a simplicial object, of course, in a simplicial model category, delta is a Yoneda embedding, and this motivates the following definition, the following correct definition of matching object in the simplicial model categories. Matching object is just a weighted limit with a weight like this, okay, and we have the following arrow, which is induced by the map of weights. We know that xn is just weighted limits, such weighted limits, and by definition, matching object is just weighted, the following weighted limits, and so we have an induced arrow. So this arrow is called matching map, and consider the following example. Suppose that X is a simplicial set. Then we know that this weighted limit is just the set of maps of simplicial sets. This is because if you have a weighted set value weighted set value weight and functor f also is a set value, then you have that weighted limit of f with a weight w is the same as the set of natural transformations between the weight and your functor. It's an easy exercise. Okay, and in this case, we see that this object is just the set of all maps between a boundary of simplex and our simplicial set. Okay, now we want to obtain the following description of matching and latching objects in terms of limits and co-limits. It is possible, and recall that we have the following isomorphism. The boundary of n simplex is just a co-limit of the following diagram. It means that we take n-1 simplices and we glue them together along n-2 simplices in an appropriate way. So these arrows corresponds to the inclusions, to the monomorphisms from n-2 into n-1. Okay, and I will use the following property, the following lemma, which is an exercise on Ninja unit lemma. Where colimits are continuous, that is, we have the following isomorphism. Where W is a diagram in the following category. It maps I into WI. Okay, and using this description and this lemma, we can obtain the following characterization of the matching object. So we know that is just end and end of the following thing. Okay, but use a contravariance of functor of this functor. This functor is a contravariant. So we have the following isomorphism. And also we use the functoriality property of the quotient of ends. And now we have this thing. After that, we can move. We can move this coproducts symbol out of the power, and thus we will obtain a product and product of ends. And after that, we use Ninja unit lemma. By Ninja unit lemma, we can replace these integrals. Oh, sorry. These integrals by the set of n-1 simplices and the set of n-2 simplices of X respectively. So we can see that we have an isomorphism matching object is a limit of the following simple diagram. And it means that it gives us strictly formulation of our intuition. For our intuition, okay, this we have the following formula, and in the same vein, we can obtain the formula for latching object. What is latching object? Let me give the following definition. In the simplicial model category setting, we say that nth latching object is a co-limit with weight with the following weight over x, and we have a latching map from the latching object to xn, which is induced by the map of weights. Okay, now we're ready to discuss some general setting and what is the Reedy categories and what is the Reedy model structures. What is Reedy model structure? Reedy categories and Reedy model structures. Okay, the category or the ordinal categories, category or category delta is an example of a so-called Reedy category, and the definition is as follows. Reedy category is a small category, say D, equipped with degree function. Okay, and also we have a wide subcategory. Wide subcategory is a subcategory which consists of all objects of our category. Wide subcategory D with this arrow whose non-identity morphisms strictly raise degree. Strictly raise degree. And also we have a wide subcategory D with the arrow inversed, whose non-identity morphism strictly lower degree. So that any arrow in the category D can be uniquely decomposed into some arrow from the category D with the usual arrow with and this composition with the arrow from the category D with the reversed arrow. Okay, for any f from D1. Okay, and example. The category delta is, of course, a Reedy category with obvious degree function. And the subcategory, this subcategory is formed by epimorphisms and this one is formed by monomorphisms. Okay. Now, for any functor, for any functor x from the category, from this category, we will write, we will denote the in the following manner. Just x of d, and we want to define the relation object and matching object, but such that we have the following arrows. The first arrow from the latching object to the xd, and the second is from xd to the matching object. And it is possible, the definition is following: the dth latching object of x. Now x is a arbitrary model category. And D, of course, D is a Reedy category. The DS latching object of X is the following colimit. Colimit of the composition of these functors. We can form the following slice category. What does it mean? It's simple notation. It means that we take the subcategory of consisting of objects which have degree less than n, and after that we can form the following slice category with the object D having the degree n. So we can form the composition with the forgetful functor. And the colimit of this composition is called latching object. And for matching object, the dth matching object is just a limit for the following diagram. Oh, sorry. Okay. we just replace this slice category by this slice category, and from the limits of this diagram. Okay, and also we will denote this category sometimes like this one. It means that we eliminate the terminal objects from this category, and of course is the same as this notation. Okay, now on a Reedy category we have the end filtration and diagrams indexed by and also maps between diagrams indexed by Reedy categories naturally defined inductively over the filtration of the Reedy category. So we can apply induction arguments for different kinds of proofs. And for example, what is the object of which have a degree 0 in Reedy category? What is a subcategory? It's this subcategory consists of discrete objects. We know that in this subcategory we have only identity morphisms, and we have no non-identity morphisms. Okay. Discrete category. And okay. And of course we have a Leschen and Mechen map by definition, because Leschen is a co-limit, hence Leschen map maps from Leschen to XD, and Mechen map from XD to Mechen. Okay, and now consider the following problem. Consider the problem of extending some functor. Some functor from some lower filtration, say n-1, to the filtration of degree n. Suppose that we want to extend this functor from the category consisting of objects of degree n-1 to the subcategory for which each object has a degree n. And we start with a subcategory consisting of 0 degree consisting of zero degree objects, and we can easily define a diagram X from 0 degree subcategory to n, we just choose for any alpha from Z some object x alpha. And as the category F0D is a discrete category, then we are done. Suppose that on the n-1 month step, on the n-1 step, we choose an object x alpha in M for any alpha from D and with a degree n. Then we should verify that each commutative diagram, commutative triangle produces commutative triangle after applying the x factor. Where the map, this map from the n-1 degree filtration and the triangle is commutative in the category of category F and D. So we should have the following commutative diagram, and it turns out that this case is equivalent to the forming the following left can extension. We can extend the factor f along the inclusion I, and it gives us the desired extension. But why we choose the left can extension? Why it's not the right? It's simple because for x alpha we have the set of co-cones, so we should choose the left can extension. We can see that the left can extension of x along I on object alpha is just weighted co-limit over this slice category with the weight, the following weight of x is just co-limit of the composition. Okay, and now we will obtain that to choose the objects, so that to choose the objects is the same as to choose the meaning of the left can extension of x along I on the object alpha. These things is equivalent, and similarly we can consider the following triangles, and they give these triangles, and here we should use the right can extension. And also the rest possible form of triangles is the following one. These commutative triangles should give also commutative diagrams like this. And we can note that the problem is equivalent to the following problem. Suppose we have a map from the co-limit of a slice category to the limit of this slice category. This one is a left can extension, this is a right can extension of alpha, and this map should factor through x alpha. We should have the following factorization. Okay, and the problem of extension of this extension is equivalent to the problem of choosing the following decomposition. Okay, and now the following theorem describes why the construction above gives the desired extension. Theorem. Suppose that D is a Reedy category, and also suppose that M is a category be complete category. That is, this category is closed under limits and co-limits, and also for N we have a diagram from N and N-1 filtration to the M, and if for any alpha from D which has the degree N, we choose an object x alpha, and we choose a factorization. From the co-limit to the limit. Then this uniquely determines an extension from F and Z to M of the diagram X. So the proof, easy proof. We must define the functor X on the maps between alpha and alpha prime, which in F and Z. So suppose we are given such a map, and we can factorize it as a composition by the axioms of Reedy category. And after that, we can just apply the functor x. We define the map as the following composition. We can do this by the above construction. We know what is the x of j with a reversed arrow and the other one. Okay, and it remains only to show that if you have a composition, then this composition produces the following commutative triangle. But you can see the details in Hirschhorn's book. It's very boring, and I decided to go into it. Okay, consider the following proposition. Let Z be a Reedy category and alpha be an object of Z and of degree n. And also we have an inclusion functor from the objects, from the n-1 filtration subcategory to the n degree subcategory. Then the first point, the Latchen category is a final subcategory. Final means that we have a preservation of we have an isomorphism between a colimit of the composition between the functor and this functor in and with a colimit of the original functor. This is from the previous talk. Okay, final subcategory of the category of the full slice category. I recall that this means that these notations are equivalent. Okay, and the second point is a dual one, formation category. Okay, and corollary from this proposition. Colimit of x under this slice category is the same as the Latchen object we know, and also we can replace this slice category with the subcategory of with monomorphism, say. Okay, and this is just a colimit of the composition x and the inclusion functor. Inclusion functor j. J is a functor which maps this category into this one. Okay, it's just a definition of final functor. And I suppose that I can omit the proof of this technical proposition, but it's quite easy. because you should just use the criteria from criterion for finality. You should just find the path between triangles. It can be easily done from the axioms of the Reedy category. Okay. And now maps between diagrams. We will construct a map F, say, between the diagrams X and Y from MD, diagrams indexed by Reedy category. The first step, we should define the map on the zero filtration, and this map is can be determined by choosing a map, any map from X alpha to Y alpha for any object alpha, because we know that these categories are discrete. Okay, and if we have a map between restricted diagrams on n-1 filtration, then we can form the following diagram. We know that this is a Latin object, and this one is also Latin object of Y. And we have a factorization, and we map into the limit. It's just a matching object and of X, and this one is a ML for Y. So the problem of finding the extension of F is equivalent to the problem of finding the this middle arrow, and the extensions of F to the N filtration of D correspond to a choice for every object alpha of degree n of a dotted arrow that makes both squares commute. Okay, and now we are ready to formulate the following important lemma, so-called Hirschhorn's lemma. If A, B, X, and Y are the diagrams in model category M, and we have a diagram of diagrams, the diagrams. And also we have some lifting which is defined on the n-1 filtration. Then we want to extend this map on the n filtration. Then for any alpha from d0 of degree n, we have an induced solid arrow diagram. And we want to find the full lifting map, but it turns out that this map are the same, but we are interested in the following case. Few words more. There is a map H for any alpha of degree n, if and only if small h can be extended over the restriction of P to the n filtration of D. Okay. In other words, if for any filtration of degree is less than n, we have a solution of this lifting problem, then we have a solution in, then if we have the solution in this diagram for the case of degree n, then we can obtain the solution for this diagram and vice versa. Okay, now proof this lemma. For any f, we have the following natural transformation between the functor L to the identical functor. Hence, we can form the following diagram. We can form the following diagram. We can apply the functor L to the original diagram, and after that, we use the natural transformations. And hence we have the following cubical diagram. But how can we form the this diagram? We should choose these maps. What are they? It's easy to form this this diagram, and we just consider the following face, facet, and we can form the push out of this facet, something like this. And of course, after that, we obtain the arrow, and so I copy this diagram. Okay, and we should understand what is the what is this arrow. This arrow can be obtained as follows. You should just so we want to construct the following liftings, and suppose that in the original diagram we have a lifting H. So after applying, we have this map, H with subscript n-1 means that this map is defined on n-1 filtration. Okay, and okay, and the map from the push out to the B alpha in this diagram is just this arrow. Okay, what is the following map? This map is from is from the property of universal property of push outs. We have the following co-cone. We can form the following composition, the following green composition, and also we can form the following red composition. The following red. Yeah, following red composition. And then we will obtain the map, the following map. Okay, and after that, we should verify that if we have a lifting in this diagram, how can I find this diagram in this cube? It's quite simple. It's quite simple. We can form the pullback in this facet diagram. Say something like this. and the pullback is here. The pullback. Yeah, pullback. Okay, and we can. So I copy this diagram and I remove some things. So I want to draw some tetrahedron. So from this commutative tetrahedron, we know that we want to prove that the map, this diagonal map from this Lifton, for this h, we can take just a small h, and we should prove that prove the commutativity of this diagram. But it can be done from observing the commutativity of this tetrahedron. But I omit the details. It looks like very awful, so I think we can skip it. Okay. This lemma motivates the following definition. Let Z be a Reedy category, and let M be a model category. And consider the map between diagrams. And if alpha is an object of D, then the relative Lattian map is the map. And of course, you can formulate the dual definition for relative matching map. Okay, and now we are ready to formulate Reedy model structure on the category MD. We say that the map is a weak equivalence, Reedy weak equivalence. If for any alpha, if this is a pointwise weak equivalence, if we have that this map is a weak equivalence in the model category M. The second point, the map is a Reedy cofibration, if for any alpha, the relative relation map is a cofibration in M. Okay, and the last one, the map is a Reedy vibration. If for any alpha, the relative matching map is a vibration in M. Okay, and the theorem of Daniel Kahn states that the category MD of diagrams, D diagrams, is a model category with the Reedy weak equivalences, Reedy cofibrations, and Reedy vibrations. And also, if M is proper, if M is a left proper, recall that left proper means that a push out of any weak equivalence along a cofibration is again a weak equivalence. If M is weak, if M is left proper or just a proper model category, then the model category is respectively left, right, proper, or proper category. Okay, consider the example. If M is a model category, then we know that this category of simplicial object in M has a model category structure from the Reedy structure of delta O. Okay, to prove this theorem, one should find those maps that are acyclic cofibrations and acyclic vibrations. We should find some characterization. And for doing that, we need in the following lemma. Suppose that for any beta suppose that we have a map between diagrams, D diagrams, and alpha is an object from Reedy category, and S is a class of maps in M. Then if for every object beta degree is less than alpha, the relative matching map the relative matching map has a left lifting property. With respect to the class S, then the induced map of Latin objects has a left lifting property with respect to S2. Okay, and the same thing can be formulated for in the case of matching objects. So prove this theorem. We will prove this theorem by induction on a degree. We know that F0 of this category has no non-identity arrows, and also we know that this category coincides with the following category. And suppose we are given a lifting problem and we want to find the lifting H, and suppose that we have a constructed H over. We will construct this arrow over this from this colimit. So suppose that beta has degree 0. Then for this object of this category, we know that the corresponding Latin objects are initial and hence are coincide, and thus the map between x beta and y beta is the same thing as the Latin map but we know that this arrow has a left lifting property versus the map from E to B, and hence we have lifting this diagram. So we have lifting in this diagram, and it follows that we have lifting in the diagram with Latin objects as from definition of Latin objects. It produces following lifting. And so we are done in the base case. The induction step, the inductive step. Suppose that k between 0 and degree of alpha, and the map H has been defined on the colimit over k minus 1 filtration. So let's take some object in this category, such that beta has degree k, and this map defines the functor between categories. As we form just a composition with the map beta to alpha. So it defines the map H on Latin object of Y, beta's Latin object of Y, and thus we have the following. Okay, and also we have the following diagram. It exists by conditions and by Hirschhorn's lemma, the lifting exists. The lifting in the diagram, in the following diagram. So by Hirschhorn's lemma, the lifting exists if and only if the lifting, the other lifting exists in the diagram above for any beta which has the degree is less than a degree of alpha. We are in the case of Hirschhorn's lemma. So so also we know that by induction we have a solution of the lifting problem for any beta with a degree less than degree alpha, by inductive hypothesis. So we can apply this. We can apply Hirschhorn's lemma above, and we can find the solution of this lifting problem. So we are done. Okay. Okay, I think that I'd like to continue this talk, say on Friday or Monday. I don't know.
Okay, great.
Now we have no time. Have you any questions, suggestions?